Hey, welcome to The Explainer. Today, we are going to break down the core concepts behind one of the most transformative technologies of our time, machine learning.
All right, so to really get this, let's first talk about what machine learning isn't. It's not what we think of as traditional programming, where some genius has to sit down and write out every single painstaking rule. In that world, we give the computer the rules and the data, and it just follows them to give us answers. Machine learning totally flips that script. Here, we give the computer the data and the answers, and it actually has to figure out the rules all by itself. Okay, so if we're not writing a bunch of explicit rules, then what's actually happening? Well, at its very core, machine learning is all about one thing: teaching a computer to find patterns on its own.
And, this really gets to the fundamental idea of why this all works. A lot of what we think of as human intelligence, like, recognizing a friend's face in a crowd or understanding what I'm saying right now, it's really just our brains being incredibly good at recognizing unbelievably complex patterns.
And that's why this is such a game changer, right? For problems where you just can't possibly write down all the rules. I mean, think about all the different ways a person can write the letter A, or all the sneaky little variations that make an email spam. We can instead just let a machine learn the underlying patterns from thousands or even millions of examples.
Okay, theory is great, but let's make this real with a super simple story. This is a perfect way to understand the most common type of machine learning, which is called supervised learning. So, here's our mission. We need to build a system that can look at a piece of fruit and correctly tell us if it's an apple or an orange. Sounds easy enough, right?
So, how do we pull this off? Well, we feed our algorithm something called labeled data. It's pretty simple, really. We show it a picture of an apple and just tell it, hey, that's an apple. Then we show it an orange and say, nope, that's not an apple. And we do this again and again and again with lots of different apples and oranges. This whole process of giving it the right answers, that's the supervision part of supervised learning.
Now, as the algorithm sees each of these fruits, it's not just memorizing them. It's actually starting to analyze their features, things like how red is it on average or how round is it. It's basically trying to create a map and put a little dot down for every fruit it sees, looking for clusters. And after a while, this is where the magic starts to happen. Eventually, after seeing enough examples, the algorithm figures out how to draw a line that effectively separates the cluster of apple dots from the cluster of orange dots. And this line, this is everything. This is the whole goal of the training. It's called a decision boundary, and it represents the rule that the machine came up with all on its own. Okay, so the training's over. The machine has its rule. But so what? What was the whole point? Well, here comes the real test. What happens when we give it a picture of a fruit it has never, ever seen before? Well, the system simply looks at the new fruit's features, puts its dot on the map, and just checks which side of that learned decision boundary it falls on. And bam! It lands in apple territory, so it makes its prediction, apple. And that right there, that's the magic moment. The machine has generalized. It took what it learned from specific examples and applied it to something completely new. Okay, let's just make sure we're all on the same page with the lingo here. The algorithm, that was the recipe we used, the set of steps for learning from our fruit data. But the final output, that specific line it drew, that's called the model. The model is the tangible thing we can actually use to make predictions. All right, so that's supervised learning in a nutshell. But learning from labeled examples isn't the only trick up machine learning's sleeve. Let's take a quick look at a couple of other powerful ways machines can learn. So, besides what we just saw, there's also unsupervised learning. This is where you give the machine a whole bunch of data with zero labels and just say, hey, find some interesting clusters in here. It's kind of like learning by discovery, great for things like finding customer groups you never even knew you had. And then there's reinforcement learning. This is basically learning by trial and error. And AI gets rewards for good moves and punishments for bad ones. This is exactly how AI gets so ridiculously good at complex games like chess or Go. Okay, but here's the thing. No matter what kind of learning we're talking about, supervised, unsupervised, reinforcement, they all share one thing in common. They are seriously hungry for data. I mean, a lot of it. And to get why that is, we need to quickly talk about something called a dimension. Don't worry, it's not as complicated as it sounds. A dimension is just a feature of your data. So for our fruit, we used color and shape. That's 2 dimensions. If we were analyzing customer data, we might use age, income, and location as 3 different dimensions. But here's the catch. While adding more dimensions seems like a good idea, more info for the model, right?
The problem is, every single dimension you add makes the data space, the universe of possibilities, grow exponentially. It gets so big, so fast, that your data points start to look like a few lonely stars in this vast, empty cosmos. And this huge problem has a super cool name, the curse of dimensionality. It basically means that as your data gets more complex, the amount of data you need just skyrockets. This is a massive issue in the real world. It's why you hear about companies spending millions just to collect and clean data. Because without enough good data to fill that empty space, even the smartest algorithm on the planet is pretty much useless. So, there's a simple rule of thumb that people in the field use. For every single feature or dimension you add to your model, you need at least 5 training examples for it. Now, just think about that for a second. If your model has 1,000 features, which is not uncommon at all, you're going to need, at a bare minimum, 5,000 data points. And this is exactly why you always hear machine learning and big data in the same sentence. They absolutely need each other.
All right, let's wrap this all up. If you're going to walk away from this explainer remembering just one thing, what should it be?
When you boil it all down, machine learning is really just this. It's the process of turning patterns from the past into predictions about the future. It finds the hidden logic and relationships in data so that we don't have to explicitly program them ourselves. It's about letting the data speak for itself. And that leaves us with one last, really powerful thought to chew on. If these systems are learning directly from the data we give them, data that reflects our world, it becomes absolutely crucial to ask what patterns, what structures, and what hidden biases from our society are we actually teaching them to repeat?